Well, the lecture for today is the signal generators. In this lecture, we will be discussing about the audio oscillators, the RF oscillators, and the RF generators. The presentation scheme will include the basic introduction to the signal generators, their types, in which we classify the audio oscillators and RF oscillators. In audio oscillators, we will be discussing the two types of oscillators, that is the RC phase shift oscillator and the Wien bridge oscillator. The RF oscillator, we will be discussing about the Hartley and the Colpitts oscillator, and finally then we will be coming to the RF generators. The signal generators, basically they are the electric instruments which are capable of generating the repetitive or the non-repetitive electrical signals. They may be in the analog or the digital domain. It is generally used in designing, testing or troubleshooting or repairing of different types of electronic instruments. Well, coming on to the types of signal generators, they are classified on the basis of the frequency range in which they generate the electric signals. They are mainly classified into two types of signal generators. They are the audio oscillators, also known as RC oscillators, and secondly they are the RF oscillators, also known as the LC oscillators. Well, the audio oscillators are further classified into two types of oscillators, RC phase shift oscillator and the Wien bridge oscillator. The RF oscillators comprises of the Hartley oscillators and the Colpitts oscillators. Well, coming on to oscillators, oscillators are capable of generating the oscillations in the form of electrical signals. Basically, all oscillators generate the sinusoidal waves. As far as the principle of oscillators is concerned, it is basically the Barkhansen criteria which we will discuss over here. Now, oscillators, they are basically the feedback circuits in which some fraction of the output of an amplifier is again fed back to the input, it is mixed to the input. Now, this mixing to the input is in two ways. It may be a mixing such that the feedback signal and the input signal are being mixed in the opposite phases. Such type of mixing is known as the negative feedback circuits, whereas if the mixing is such that the feedback signal and the input signal are being mixed in the same phase, then it is said to be the positive feedback. So, oscillators are basically the feedback circuits having positive feedback. Moreover, in order to act like an oscillator, it should have one more property in which we say that the product of A and beta should be greater than or equal to 1. Here A is the gain of the amplifier and beta is the feedback factor of the feedback signal. If the product of the gain and the feedback factor is greater than or equal to 1 and as well as the circuit has positive feedback, then we say that the feedback circuit is satisfying the Barkhansen criteria, and now it is capable of generating the oscillations. When the Barkhansen criteria is once fulfilled in the feedback circuit, there is no need to feed an external input into the circuit. The feedback signal itself acts as the input signal and a repetitive cycle is generated, thus producing the oscillations at the output. Obviously, the gain of the amplifier A can be calculated as the ratio of the output signal to the input signal, whereas the beta, which we say as the feedback factor, is the ratio of the feedback signal voltage and the output voltage, it is Vf upon Vo. Whether it is the RF oscillators or the audio oscillators, they both are based on the Barkhansen criteria only. Now, coming on to the audio oscillators always produce sine wave signals in which both the amplitude and the frequency can be varied. The maximum amplitude of the output waveform is typically of the order of 25 volts, RMS value I am talking of, whereas the range of the frequency covers is at least the audio frequency range, that is that from 20 hertz to 20 kilohertz, and that is why they are called the audio oscillators. Now, there are two types of audio oscillators, RC phase shift oscillator and the Wien bridge oscillator. We will discuss both these oscillators one by one. First of all, coming on to the RC phase shift oscillator. Now, the nomenclature as RC oscillators has been done because the feedback circuit here comprises of the RC circuit. It is the resistance and a capacitor based circuit. So, we call them as RC oscillators, and in the RC phase shift oscillator, the feedback circuit obviously it comprises of the RC combination, but there are 3 RC combinations. We will be coming on to it later on about why 3 RC combinations has been used after discussing the basic circuit. Now, the basic circuit comprises of an amplifier, which is basically a common emitter amplifier, as we know that it always produces a phase shift of 180 degree. The output of this common emitter amplifier is then fed to a phase shift network, which comprises of a combination of R and C. 3 RC combinations has been used. Now, since the common emitter amplifier is producing a phase shift of 180 degree, and in order to have a positive feedback, the feedback circuit should also produce a phase shift of 180 degree, thus producing an overall phase shift of 0 degree or 360 degree and creating a positive feedback loop. So, we need that the phase shift circuit should produce a phase shift of 180 degree, and that too with a RC combination. We know that ideally RC combination can produce a phase shift of 90 degree. So, ideally we require 2 RC circuits in order to have a total phase shift of 180 degree, but this is when we are talking of the ideal RC circuit. In practical circuits, we use 3 RC circuits, and the values of R and C are so chosen that each of RC combination produces a phase shift of 60 degree, thus producing a total phase shift of 180 degree, and that is how the positive feedback is achieved. Now, the values of R and C of each RC combination are all same, means in all the 3 RC combinations the value of C is the same and the value of R is also same. So, we came to the conclusion that the positive feedback has been obtained in this circuit. Now, this 180 degree phase shift which has been produced by the phase shift circuit is obtained for a single frequency only. So, we find that the Barkhansen criteria, or we say that this positive feedback is being obtained only for a single frequency, and this will be the frequency of oscillations which will be obtained at the output. Now, since the Barkhansen criteria regarding the positive feedback has been fulfilled for a particular frequency only, the frequency at which the RC circuit is producing a phase shift of 60 degree, each RC circuit is producing a phase shift of 60 degree. Now, that will be the frequency of oscillations. As far as the other condition, that is A beta should be greater than equal to 1 is concerned. Now, going through the mathematical analysis, we find that the value of beta comes out to be minus 1 upon 29. Here negative sign indicates that the feedback circuit is producing a phase shift of 180 degree. Now, since beta is minus 1 upon 29, so the gain of the amplifier, that is A, should be greater than or equal to minus 29 in order to satisfy the condition that A beta is greater than or equal to 1. Now, A is also considered to be negative, A is also taken to be negative because the amplifier is the common emitter amplifier and it is also producing a phase shift of 180 degree. So, the required condition is that the gain of the amplifier should be greater than or equal to 29. So, in order to satisfy the Barkhansen criteria, we conclude that in case of RC phase shift oscillator, each RC combination should produce a phase shift of 60 degree, as well as the gain of the amplifier should be greater than or equal to 29. But as far as the RC phase shift oscillator is concerned, its frequency stability is not as good as that of the Wien bridge oscillator, which we will be discussing next. The distortion is greater, and moreover, if we want to change the frequency of the RC circuit, then we have to vary all the three values of RC. If we want to change the frequency of oscillations, then we have to change the value of all the three C and all the three R's of the three RC circuits, and the variation, simultaneous variation of all the three capacitors and all the three resistances is a tedious job to be done. So, varying the frequency is quite a difficult job in case of RC phase shift oscillator. Coming on to a better oscillator, better audio oscillator, it is the Wien bridge oscillator. The circuit here shows the Wien bridge oscillator, wherein we have used two stages of amplifiers in this circuit. Two transistor amplifiers has been used, obviously in the common emitter mode. Now, since two common emitter amplifiers have been cascaded, the overall phase shift of this amplifier circuit, of this two stage amplifier circuit, is 360 degree. In order to have a total phase shift of 360 degree, that is positive feedback, the feedback circuit should produce a 0 degree phase shift in order to have the positive feedback. So, we have used the bridge over here comprising of the RC combinations in the two arms, and the other two arms are R1 and R2. One of the arm is the series combination of R and C, and the other arm is a parallel combination of R and C of same values, and the other two arms are R1 and R2. So, the values of R and C here are chosen such that the bridge circuit or the feedback circuit produces a phase shift of 0 degree. Now, this 0 degree phase shift is also achieved at a single frequency. Therefore, what we say that only for a single frequency the positive feedback is being obtained, or in other words we say that only for a single frequency the positive feedback and the Barkhansen criteria is being fulfilled. So, when the oscillations will be obtained at the output, they will be of the same frequency for which the feedback circuit is producing a phase shift of 0 degree. Therefore, the feedback circuit in both the cases, in RC phase shift oscillator as well as in Wien bridge oscillator, we find that the frequency of oscillations at the output of these audio oscillators depends upon the feedback circuits. So, by varying the value of R and C, we can vary the frequency of oscillations. The frequency of oscillations in these Wien bridge oscillator is given as 1 upon 2 pi R C. These R and C are the values, as discussed earlier, are the values in the bridge circuit. Now, in this case, in the Wien bridge oscillator, the value of beta calculated is 1 upon 3. It is a standard that in Wien bridge oscillator the feedback factor always comes out to be 1 upon 3. So, in order to satisfy the second condition of A beta greater than or equal to 1, the value of A should be greater than or equal to 3, thus satisfying A beta greater than or equal to 1. Note that here the value of beta is positive, and so is the value of A. Beta is positive because the feedback circuit is not producing any type of phase shift, and moreover the value of A is also positive because the total phase shift produced by the two stage common emitter amplifier is 360 degree or 0 degree. So, A is also positive, beta is also positive. So, comparing both these oscillators, we find that in case of the RC phase shift oscillator, the gain of the amplifier required was 29 or more than that, while in case of the Wien bridge oscillator, the gain of the amplifier required is 3 or more than that. Now, coming on to the RF oscillators, they are also called the LC oscillators, because the feedback circuit here comprises of the inductor and capacitor, unlike the case of the audio oscillators in which the feedback circuit was comprising of the RC circuit. RF oscillators are also called the LC oscillator. An RF oscillator produces signals in the radio frequency range. Now, the Barkhansen criteria is also the condition that should be satisfied here also. The phase shift network of RF oscillators is an LC network. The LC combination, which is generally referred to as a tank circuit, it acts as a filter to pass the desired oscillating frequency. The tank circuit is designed to be resonant at the desired frequency of oscillation. An LC circuit is said to be resonant when the inductive and the capacitive reactances are equal. So, when the resonance occurs in this tank circuit, then the frequency for which this resonance is occurring, simultaneously this tank circuit will also produce a phase shift of 180 degree for that same frequency. So, if we are using a common emitter amplifier which produces a phase shift of 180 degree, then the LC oscillator, that is the feedback circuit, will also produce a phase shift of 180 degree, thus producing positive feedback, but the LC circuit will produce a phase shift of 180 degree only for that single frequency for which it resonates. So, again we are going to obtain the oscillations at the output of this circuit only for that frequency for which the tank circuit or the LC circuit is producing a phase shift of 180 degree, and this frequency is equal to the resonance frequency of this tank circuit. Although there are a number of standard RF oscillators in use, but the most popular are the Colpitts oscillator and the Hartley oscillator. The Hartley oscillator, it uses two inductive coils which are in series with each other with a capacitor in parallel to the series combination. Everything is same except that the feedback circuit here comprises of L and C. Two L1 and L2 coils are connected in series. Now, these two coils in series are now in parallel with the capacitor, and the frequency at which the resonance occurs, at that frequency only this circuit produces a phase shift of 180 degree, thus satisfying the Barkhansen criteria of positive feedback, and for this frequency we obtain the oscillations at the output. Now, this frequency is given as 1 upon 2 pi root L1 plus L2 plus twice of M into C, where L1 and L2 are the self inductances of the coil and M is the mutual inductance between the two coils, since they are placed close to each other, and C is obviously the capacitor in parallel to this L1 and L2. Now, coming on to the Colpitts oscillator, the circuit is almost similar to the Hartley oscillator, only with the difference that instead of two inductors and one capacitor, here the tank circuit comprises of two capacitors and an inductor. The two capacitors are in series with the inductor in parallel with it, and the frequency of oscillations obtained for this circuit is 1 upon 2 pi root L, and since the two capacitors C1 and C2 are in series, it comes out to be C1 C2 upon C1 plus C2. The whole of the working is same, the common emitter amplifier producing a phase shift of 180 degree and the LC circuit comprising of C1, C2 and L1, they produce a phase shift of 180 degree, but only for a single frequency, that is the resonance frequency. So, the frequency of oscillations obtained at the output of the LC circuit will be 1 upon 2 pi under root LC. Depending upon the values of L and C, we can vary the frequency at the output of these oscillators. Now, coming on to the RF generators. RF generators are designed to provide an output signal over a wide range of frequencies from approximately 30 kilohertz to nearly 300 megahertz. The term generator is generally used for an instrument that is capable of providing the modulated output. Here the output may be a simple oscillating output, or it may even be a modulated output. If the oscillator is such that it also produces modulated output, then instead of saying it to be an oscillator, we call it as generator, that is the difference between the RF oscillator and the RF generator. The following circuit shows the block diagram of the RF generator. The exact frequency is selected with the frequency selector circuit of the oscillator. The frequency stability of this generator is limited by the stability of the LC oscillator circuit. Therefore, considerable attention should be directed towards the designing of this master oscillator. This master LC oscillator, it should have a good stability, because the stability of this LC oscillator will decide the stability of the whole RF generator. The sinusoidal output of the oscillator is then applied to the broadband amplifier that amplifies the signal and provides buffering between the oscillator and any load. So, any type of loading effect is eliminated by the use of the broadband amplifier. If desired, the RF signal may be modulated even, and moreover the beauty is that we can control the modulation frequency as well as the percentage modulation. The amplifier output is then applied to the attenuation network. The output of the network is attenuated as desired, and simultaneously the output is measured by the output meter. The entire instrument is contained in a shielding cabinet, so that the external noise cannot disturb the generated frequency, and the instrument provides the modulation as said earlier, may be amplitude modulation, frequency modulation, depending upon the type of RF generator. So, in this lecture we have discussed the different types of signal generators. Firstly, we discussed about the audio oscillators, which generates the oscillations in the audio range from 20 hertz to 20 kilohertz, and in the audio oscillators we have discussed the RC phase shift and the Wien bridge oscillators, saying that the Wien bridge oscillator is a better option than the RC phase shift oscillator because of the stability, and moreover the output frequency can be adjusted easily in case of the Wien bridge oscillator. Moreover, the gain of the amplifier required in case of the RC phase shift oscillator is 29 or more than that, whereas in case of the Wien bridge oscillator the amplifier gain may range from 3 or more than that. Then we have discussed the LC oscillators or the RF oscillators, which are capable of generating the oscillations in the frequency range of radio frequency, high frequency range, and where we have discussed the two types of oscillators, the Hartley oscillator and the Colpitts oscillator. Well, in both these oscillators there was a common circuit. The feedback circuit commonly comprised of the LC circuit, and the LC circuit is said to be the tank circuit, and the resonance frequency of this tank circuit decides the frequency of oscillations, or rather we say that the frequency of oscillation is equal to the resonance frequency of this LC circuit, and not a major difference was there in Hartley and Colpitts, except that in Hartley there were two inductor coils in parallel in series with each other with a capacitor in parallel, and in case of the Colpitts there were two capacitors in series with each other with an inductor in parallel to it. And then we finally discussed the RF generators, where we say that along with the oscillating output, the generators are also capable of producing a modulated output, maybe a AM wave or FM wave, depending upon the type of generator we use. So, that is all, and hope you might have enjoyed the lecture. Thank you.